Hi everyone. So in this video we discuss other versions of gated units other than the LSTM, and hopefully this discussion will help you gain insights about some of the important challenges when designing a gated unit. So the first is called gated recurrent unit, and the abbreviation is GRU. And a gated recurrent unit has an update gate and a reset gate. Right? The update gate implements something similar to what leaky units do. So the update gate controls how much the previous state, or how much the state at time t minus the value of the update gate at time t minus 1 determines how much the value of the state at time t minus 1 will pass over to the value of the state at time t, and how much the complement of the update gate will determine how much the input will affect the state, right? So here the state at time t depends on the inputs up to time t minus 1 in the notation here in that example. So ui of t minus 1 determines how much I would allow hi of t minus 1 to go into hi of t, and 1 minus ui of t minus 1, the complement, right? So ui is between 0 and 1 because all these gates are determined by a sigmoid. So the complement will determine how much the input after passing by a nonlinearity that is also a sigmoid will affect the state, right? Now, so you have ui of t minus 1 times hi of t minus 1. ui itself is determined by a sigmoid that has a bias unit biu, right? And weights uiju that determines how the input affects the update gate, and weights wiju that determines how the state determines the value of the update gate, right? Now let's go to the input nonlinearity, which is a sigmoid. There is a bias unit bi and weights uij that determines how that are connected to the input determines how the input affects the state, and weights wij that determines how the previous state affects the current state, right? So it's either I keep the past state if uit minus 1 is close to 1, or I have a factor that basically determines on the input and the past state as well, right? But the past state here in that other input, if ui of t minus 1 is close to 0, now that depends on something called the reset gate, right? And the reset gate has a very important function, is that it allows you to filter out the previous state. So not necessarily all the dimensions of the previous state will affect the current state, right? So depending on the values of the vector, right? So depending on that vector given by the reset state, right? Some of it will weight the previous states differently before multiplying by the weights wij, right? So you can think of the reset state, basically this is the mechanism of controlling that the gradient doesn't vanish or explode by resetting the value, by resetting the connection between the previous state and the current state, right? So you have the ability to disconnect some of the dimensions of the previous state from affecting the current state through the reset gate, right? So to summarize, so clearly it has less gates. An LSTM has 3 gates. Here we have 2 gates, which can speed things up, can simplify the functionality, but also you can think of an LSTM as more flexible or more powerful than, like in terms of expressive power, it can represent more functions than a GRU, right? So this is one. So there are variants of GRUs itself. So you can implement GRU with sharing of reset gates over multiple units, but you can also implement LSTM with sharing of forget gates over multiple units, and you could also have some kind of global control over the whole layer that consists of multiple GRU units or multiple LSTM units combined with a local control on a unit by unit basis, as we do here, right? So maybe you would have some parameters that are determined by the whole layer, right? By the inputs to all the units, right? By the states of all the units in the layer, Okay? So that's the GRU. Another variant that is very powerful in terms of computational efficiency is called simple recurrent units, and the abbreviation is SRU. And they are basically faster whenever graphical processing units and the CUDA environment specifically is available, because they do a lot of optimizations that make things a lot faster at the cost of possible reduction in accuracy. Because the main mechanism in simple recurrent units that make it faster is that the multiplication by the previous state, so here this Wij matrix when multiplied by Hj of t minus 1, this is done instead of a multiplication that depends on all the elements of the previous state or all the dimensions of the previous state simultaneously. It's done through element-wise multiplication. So clearly, this is a much simpler operation, right? So if I multiply a weight just by element-wise by the dimensions of the previous state, right? But so that takes from the expressive power. So maybe I cannot represent some functions that I could have represented with GRU and LSTM, but it can speed things up significantly, because you could parallelize over the graphical processing unit the computation corresponding to the state-to-state transition over the different dimensions. So you could compute the different dimensions separately by doing the state-to-state transition element-wise, right? And another mechanism in SRUs is that they include what's called highway connections. And highway connections basically is a simple way of implementing a skip connection over time, right? You could, if you're curious, you could read about them separately, even about highway connections themselves, or the paper that introduces simple recurrent units. So in general, I hope that gave you an idea of the challenges that the state-to-state transition can be a bottleneck, right? So for example, in an LSTM, the computation is order L, which is the length of the sequence, times B, which is the batch size, times basically D, which is the dimensions of the state vector, right? Times D squared for LSTM. In SRU, so for LSTM, it's order L, B times D squared. And L here is the length of the sequence, B is the batch size, D is the dimensionality of the state vector. For the SRU, it's order L, B times D, right? So this is for SRU, and this is for LSTM. So basically, it reduces the dependence on on D, which is the dimensionality of the state vector, from square to linear, right? And that ends up in many practical situations making things much faster when using SRUs, at the cost of like slight reductions in many cases in accuracy due to the element-wise multiplication of the state-to-state transition. Thank you.